Okay, so hello everybody, welcome to BERT. So we just had a small presentation about the transformer and attention is all you need, and now we will switch to sorry, yes exactly. So we will switch to BERT, and we'll see how we can use this transformer for more useful tasks than translation. We'll see how we can do more tasks with it. So BERT actually stands for Pretraining of Deep Bidirectional Transformers for Language Understanding. It's a very fancy title, but it's just that's it. I can get the word BERT out of it. It was submitted in 2018. It has over 10,000 citations. So it's one of the most important papers in NLP and one of the most cited one at least. And it's been written by people from Google AI Language, including these 4 authors. So let's go over it. And so we will first start with a little bit of background on NLP, and then we will go to the structure of BERT, and we'll finish with some pre-training and fine-tuning. The pre-training and fine-tuning phase to be able to use it on different tasks. And then we will end up with the complexity and analyze the actual mechanism behind what is BERT actually learning. So first, at the high level, let's start what do we want to do in NLP and what is the goal and things like this. So we would like to understand, at the high language, NLP is trying to understand language and especially sentences and be able to solve tasks that use language. And one could say that to understand a sentence, a good idea is to understand the actual meaning of the words inside a sentence. This makes sense, right? So let's try to do it. And the first way to try to associate a word to a certain meaning in a mathematical way would be to create a mapping between word and vector. The problem with this technique is that it's very nice, but we have some words have some issues. Like the most obvious one are homonyms, like address to a nation, or the address of my house are the same words in this context, but have a different meanings in this context, and this is problematic. And also words which have references to other things have a different meaning because it references to some different ideas. And so one idea that we can still use this mapping because this embedding is still very useful, especially if you learn on it, to make sure that similar words are close to this vector space and different words are very distant from each other. And then we pass it through a special function, and then we take these embeddings and we pass it through a special function such that it contextualizes this embedding, and we get the actual true meaning. So this is a good idea, and this is what BERT is doing at a high level. It's just taking words and giving out some vectors which are supposed to be close to the actual meaning of the word, to the contextualized meaning. There have been some different techniques on how to do it properly, actually. Oops, sorry. And the different techniques here are the first problem is that we need to learn different things on a sequence of variable length. And now the issue with this technique is that it comes exactly in a variable length because sentences don't have one fixed word. Otherwise, we could more or less just put it inside a feed-forward neural network, and then we would be more or less done. But so instead of being able to do it, we are not able to do this, so we have to come up with a new idea, and the most basic idea is the recurrent neural network. And here the idea is that we take each time one token and the previous hidden state and compute the next hidden state, which also associates to the new embedding of the token. This is the most basic idea, and then we iterate over all the tokens, and we get for each time the corresponding hidden state, which is the output for each token. And the RNN has some issues with vanishing and exploding gradients, so people came up with the LSTMs, which stand for long short-term memory, and this improves the RNN in quite a significant way, especially as this memory cell, which is also transmitted in each iteration. And the computation, what we actually are doing is that we are checking if we have this memory cell, and we are trying to figure out if we should overwrite it, by how much and by what. These are more computations that are done, but we will not go into details. So then some people came up with a good idea of trying to use these LSTMs to do a contextualized embeddings, because now we can put the LSTMs and we can pass it through all the embeddings of our word and try to get a new final embedding. This is what Elmo is doing. It's taking our embeddings. It has 2 layers of LSTM. They go from, in this case, they go to right from left, and they also have other LSTMs which go left to right. And they have been pre-trained, because this is already in NLP. This is a very strong idea that we have so many words, dictionaries, Wikipedia, which are full of data, of unlabeled data, but they already give an idea about the structure and the likelihoods inside sentences. And so Alma uses these LSTMs to make a contextualized embedding, and at the end, for each word, we take a linear combination of the different layers to output the final embedding. But there are still some problems because the LSTMs kind of struggle with very long dependencies, and this makes sense because if you, for example, we want to send a message, or some memory, some information from the first word to the end word, it takes O of n steps, because each time we have to go from the first to the second to the third to the fourth, and spreading this over very long dependencies, our model doesn't really manage to do this very well. But Elmo is already a very powerful paper, and it really sets this idea of pre-training, also of bidirectionality in the embeddings, and of contextualized embeddings. But so yeah, it would exactly also be better that we could spread information in a constant size step. And then there were some new ideas and some ideas in NLP which came around, which is called the attention mechanism. This is a very powerful idea, and we'll see how it makes sense to try to apply it. So what does it do? It does that we have multiple hidden states. Let's say we want to translate a sentence in French to English, for example. And for each of the sentences in French, we compute a certain hidden state. In this case, it would be je suis étudiant. Now we compute through some arbitrary way, let's say, some scores, which tell us, if we are trying to first translate the word I, it tells us which one of these words is the most relevant one. And here, for example, it's je, which makes a lot of sense because these two are equal words. And so it gives a lot more weight. It says that the hidden state one is way more important than the other ones. So let's give it a lot more weight. And when we try to do the final prediction, we give this one way more weight. Now one could think, it's most likely to always be a diagonal. This is mostly true, but it can sometimes understand some very, not difficult, but complex ideas, one could say. So here we have a diagonal, and the diagonal, here I have a diagonal, and which is flipped 90 degrees, and this exactly comes from a very good attention mechanism, because here we're trying to translate Zone économique européenne to European Economic Area, and this is in French, and actually in French it's flipped around. It's the other way than European Economic Area. So here they flip around the diagonal. So in a way, this attention mechanism is able to understand this subtlety from the French language. So that's the example of a good attention mechanism. Now, how can we use this? So now you just had this presentation. Attention is all you need, and this is exactly what that attention is all you need is doing. It is able to learn these attention mechanisms and is able to make good translations. For that, it uses some encoder layers, which take as an input all these the word which you're trying to translate, and decoders which one step after the other predict the next word of the sentence. And it was very powerful. It uses the attention mechanism and introduces this transformer, which is these encoders and decoders, and it's able to learn these attention scores. And it's also relatively parallelizable, which makes it even more powerful. So, so let's dig a little bit into how they work and how we could use them. Because in a way, if you think about it, if we go back to this attention mechanism, it makes a lot of sense. Like if we're trying to contextualize an embedding, for example, to the word to or he or she, would usually have a reference to some other things, some other ideas in a sentence, then it makes sense that we give way more weight to some parts or some other parts of the sentence, right? So this attention mechanism seems to make a lot of sense. So already it gives a nice, not really theoretical, but a nice intuitive idea on why it could be a good idea to use them. So let's see how can we use them. It's already not sure, like how it's really nice, but how do we use them? So let's take the encoder parts of the transformers, and let's try to train this encoding, because we would like to use this attention as all you need paper. We want to use these transformers, but we don't want to have we don't want to do translation. We want now to stick to English and stick to one language and avoid any problem. But also, if you think about it a little bit differently, these encoder layers, they're encoding the input, and then they pass through the decoder and come out in a new language. So at a high level, what is happening is we're taking English words, going to a vector space, and then going to French words. So this vector space in between should have a very good understanding, with a good representation of what the actual word is meaning. And it should be heavily contextualized, because it's very important in translation. So one could think, okay, these encoder layers are exactly the ones that generate this vector space. So let's try to build it and use them. Now, how can we do that? So for that, let's dig a little bit into the structure of these encoders. So how do they work? It's quite easy. They take the embedding, they pass it for a self-attention layer, which we'll see after. They give a new embedding and then a feed-forward neural network, which we learn, and we have the final output. So now, how does this self-attention mechanism work? That's exactly how we're going to see it. Here, oops, sorry. So they work by taking the embedding. So we will go for an example, and here we try to give the outputs of thinking and machines. So we take the embeddings. For now, we'll assume that our words are already embedded. We will see how BERT actually does this embedding, but we compute the query, the key, and the value vector out of this embedding. And then if we're trying to create the output for thinking, we take the query key of thinking and multiply it with, and make the dot product with each of the keys of each word, and we get a score. And then we divide it by some value. This is just to get a variance 1 in the attention is all you need paper. And this is, we passed for a softmax. And this is the raw attention score, like really, like this shows how relevant this word is. And then we create a weighted sum to get our output. We do this with all the vectors, and here you see, because we are multiplying each time with the query with the key of each value of each vector, we see that to the end of the sentence or to any part of the sentence, we will always have it will always take O of 1 for the information to flow. So how do we learn and how do we compute these query key and values vectors? We are actually learning the key, the query key and value matrices, which convert our embedding to these special vectors. Here it's in block formation, such that everything is in matrix. And then we have at the end our final formula is this. So this is called an attention head actually. And the thing is that maybe we would like some different matrices which maybe capture some different ideas, and we call this multi-headed attention. We just put multiple of these together and we concatenate our results, and then we get here, for example, we have 7 attention head with 7 different matrices which we learn, and we concatenate them to the final result using another matrix which we also learn. So that's the encoder. So now we can build BERT. BERT is just stacking 12 of these encoders together, and yes, I mean, for BERT base, of course, one can adapt the number of encoders one wants. BERT large uses 24 layers actually, and BERT base has roughly 110 million parameters, which is roughly equal to OpenAI GPT, which is the paper which is quite different from actually, they compared a lot in the paper, but it's very like, I personally believe, and I've talked about it also with some other people, is that this doesn't make a lot of sense because OpenAI GPT is really a different model. It's really more of a language model. It's trying to predict the next token in a sentence. It's not really trying to understand sentences. And and this is, but it has been the one which has been setting most of the state-of-the-art scores on different benchmarks. So let's instead try to tokenize. So now the problem is that we saw that we have these embeddings, but we first need to do them. How do we do this? That's quite easy. We use the usual tricks, is that first we tokenize the sentence. For example, if you would like to tokenize he likes playing, we always first would set the CLS token, then he, it's another 30,000 tokens, because we learned exactly 30,000 tokens. How do we learn them? We use something very similar to bytecode encoding. It's called word-piece embedding, and it's also quite a powerful idea, but it's also heavily pre-trained, and then we have 30,000 tokens. Then here's an hour token, likes is an hour token, but then playing is not an hour token. So what we have to do is that we have to split it up. We have play an hour token and double hashtag ing an hour token. The double hashtag means that exactly we just split the word in 2 parts. Then we put a separator because each time we input at least 2 sentences. This is very important. So what do we do now? We have the input embed. Sorry, excuse me. So, sorry. So we have the input embed. Now we have our token, and we have our word which has been tokenized, and we now use the token embedding layer, which converts our token to vectors, which we learn during the whole pre-training phase. And we also have some segment embeddings because, as I said, we always put 2 sentences in our model, and this allows us to say which word is to which model, which word is to which sentence. And position embedding is because if you think about it, and we saw it in the previous presentations, that the transformer doesn't really have a notion of where which word is, so we have to have a special position embedding such that it can understand. So now, how do we train it? That's a good question. We use a pre-training, and then how do we solve different tasks? For that is the fine-tuning phase. But the pre-training phase is the most important one. It's where we use all this unlabeled data to be able to understand what BERT is actually doing, such that BERT gets a good understanding of actual language. So for that, we have a first task which BERT is trying to solve. And the thing is that if you think about it, BERT is really not able to capture well. It's not able to generate any text. There have been some techniques which try to do it, but in the pre-training phase, it's really unclear how we could pre-train it on text generation, which have been models like OpenAI GPT and stuff like this. They've been heavily doing. So instead, the next word. So instead, we will use next word prediction. And sorry, we will use a masked language model. And how does this work? The idea is quite easy, and in a way it's relatively obvious, is that we just mask a word in our sentence and try to predict what it should be using its embedding, using its final embedding. So that's what it's doing. But if you think about it, there's still some issue if we would only do this and only apply this special mask at one position of the word and then do the prediction. Then there's a little bit of inconsistency because in the fine-tuning for zone different NLP tasks, this mask token never appears. So this is a big problem because our model would more or less only learn to apply this prediction, to do this prediction process and do the correct embedding only when it has the mask token, which it will never see again after. So instead, we will use a technique which we will use a mask token. We will consider token masked with probability 0.15, and when it's masked, we replace it with 10% of the, we replace with a random word 10% of the time, never change it 10% of the time, or actually apply the mask token 80% of the time. Now, how does this work? So now, that's not how this works, but they try to change a little bit these scores, and they roughly have some differences, which are plus or minus 2% on their final scores and the performances. So it's not so important, but it's already good. And so we are more or less always learning to do the embedding, always. So it's learning that it should always do it, because the last function is always on all the mask token, not only on the token which has this mask. So we do it on all the mask token. It's a little bit different from autoencoders, which would try to do it on all the tokens, but so here we only do it on these ones. So that's the first part of loss function. We also have a second part of our loss function, is that we would like to understand the relationship between sentences. And as we said, we have always 2 sentences in our model. And so what we do is that we take sentence A and sentence B, and we use the final embedding of the special CLS token, which we inserted at the beginning, and we try to make it predict using a neural network if these 2 sentences logically follow. For example, the sentence today is very cold, I should get a jacket. Today is very cold, I will buy a jacket, makes a lot of sense. Or today is very cold, I need to buy some sunscreen, doesn't make any sense. Unless you're someplace, but okay, let's say it doesn't make any sense. And so yeah, these are the 2 parts of our loss function. And let's train this model. So now this model is actually trained on Wikipedia, and also on some giant book corpus. With this pre-training, we will see a little bit how much time it takes, but a little bit after. And first, let's see how can we use this to solve these tasks. So one of the first benchmarks, and one of the most obvious one, is swag, which gives 4 possible continuation of a certain sentence. And one could think that in a way we are cheating, not really cheating, but this is exactly what we have been doing in the second part of the last function. So our model should be very good at this. And what it does is that it takes the output of the CLS token and computes the confidence score using it makes a dot product with a learnable vector, which we learn during a small fine-tuning phase of the model, such that it can really adapt to our special needs. So BERT large always completely destroys Elmo, and it's already way, way better than GPT, and it also starts to get better than humans experts, unless humans cluster together and start to solve the task together, which in a way actually the attention heads, because we're using 12 different attention heads, in a way BERT is also using multiple attention heads. So it has multiple humans, so to say, if you could say that the human is attention head. But okay. So let's move on to the second task. But here we have, this is a first benchmark, and this is quite easy to see that because it's really part of the last function, our model should be quite good. Let's go to something which can be relatively unintuitive, and it's really quite unclear why BERT is so good at it. And actually, BERT is very good at SQUAD. What is SQUAD? SQUAD stands for Standard Question and Answering Dataset. And here we're given an answer and a paragraph which contains the answer to a question. Now here we are trying to predict if the answer. We are trying to predict where the span, where the answer lies in our text. We have to delimit the span of the answer. So for that, we have a start and an end vector, and we all these predict a confidence score on how confident we are that the answer starts here or ends there. And we do that by doing the dot product, and we fine tune it on special. We do some fine tuning phase to try to learn these vectors. And our model is quite good. They actually use some additional pre-training and some additional fine tuning, and our model is already better than humans and way better than Elmo. So now let's move on and let's go back a little bit. How complex is this model? It's a very nice model, but it's actually hugely complex. It took them was using 16 TPUs. It took them 8 days to do the pre-training on BERT large, and it's also, even doing inference time, it's really a complicated method, and that's actually quite a problem. And now the thing is, using there have been some techniques which try to optimize it, and companies have also been trying to optimize this. And one of papers which really brings a nice idea is that where they try to use a very large batch size, and the previous techniques which were doing this were using something called large, like layer-wise adaptive learning rates, but it performs really poorly with attention models. They have to come up with a new model with a new method which is called LAMP, which works well. Using 1024 TPUs, so that's already way more than 16. They managed to bring it down to 76. And NVIDIA used the same paper, but trying to do some advertising for their DJX superpods or something like that. It brings it down to 47 minutes. And now the record is held by DeepSpeed of Microsoft, which takes 44 minutes. And actually, I recommend that you read the blog post of DeepSpeed, because it shows really how crazy things can get, and really crazy how these optimizations can get, which in a way could call for the dissociation between coding and performance optimization for hardware specific architectures. And this is actually a very interesting topic, which is actually what I'm doing on bachelor thesis, but so let's not talk about it here. And there have been some different techniques to try to optimize BERT and just throwing more GPUs at it, because GPUs is not a free and unlimited resource, and except for companies like NVIDIA. They try to fix this issue they try to fix issues with BERT. So Robert A is a good example of it, and Robert A is doing it by optimizing a little bit, and also shows that BERT is actually on a trainer. So what is it optimizing exactly? It's using something called, so one of the first techniques, what is it doing is dynamic masking. The idea is that when BERT is trained between each epoch, the masking is always the same for each sentence. So in the dynamic masking, they change it between each epoch. They also increase a little bit the batch size to improve the training, and they show that BERT is actually severely undertrained. Oh, and sorry, they also input full sentences, because we always input 2 sentences during the training phase in the original BERT paper, and now they input more than 2, because it makes more sense. If you think about it in the SQUAD data set, you get way more than 1 sentence, so it makes sense to make more than 1. And they show that BERT is actually severely undertrained. We go from 13 gigabytes to 16 to almost 160 gigabytes, and they pre-train it even longer, and they improve all its score. And if you think about this, this is really kind of a problem. I mean, it shows that BERT is actually severely, not undertrained, but severely data inefficient. Like just throwing more data, just putting more epochs, just putting more, it improves. So in a way, 160 gigabytes of data is already 13 gigabytes of text, like I'm talking text here. This is like stuff which is super easy to encode. it doesn't take, so 13 gigabytes is already a huge amount of data, and 160 gigabytes is even more. So there's really like an efficiency question with BERT, but it's actually not just with BERT, it's more general. Here it's, I think OpenAI GPT is the best representation, and going from GPT to GPT-1 to GPT-2 to GPT-3, it's just more or less trying to increase the size of it and training even longer, and it always improves better. And so this really questions in NLP, like how data efficient are these models. And actually, there have also some blog posts by Yann Lequin, who is the father of machine learning. I think you know him. And they also, not a blog post, but you also argue that these models no longer make much sense. I mean, it doesn't make much sense to try to always increase the models, pre-train them even longer to try to get a breakthrough in the performance. But the thing is that they always improve. They don't improve a lot, but they keep improving. So let's go to some other paper which tries to also understand BERT, and it actually tries to understand how these attention heads work. So this is a paper made by Stanford and Facebook, and in this paper they look at these attention heads in details. So what do they found? So they found that a little attention already is given to himself, to the word himself. This makes a lot of sense because often when we were training it, we put a mask token on it. So it would be good that at least it's a good idea that at least it makes sense that it shouldn't put too much attention on him, because most of the time it doesn't include any useful information about the word itself. So this makes sense. Also see something that most of the attention actually goes to CLS and separator token. And this is actually, they try to argue why. They have different explanations, but the strongest one, and they try to show why it's true by using by analyzing the gradients and things like that. They show that actually when an attention head is doing a certain operation, some certain attention mechanism, it's doing some certain operation on attention, the thing is that it's doing the special operation, and sometimes this operation cannot apply. Like if you're trying to attend an object to its verb, and our word is neither a verb nor an object, then there's nothing to do. The operation does not apply. So they use the CLS and separator token as some sort of neutral element, like nothing to see here, no operation is going on. That's what they're doing, more or less. And especially analyzing these attention heads show that actually it has a really good understanding of English, like really advanced, and they actually train it on some. They actually show that using on some labeled data set by the Washington Post, it is really able to have an excellent understanding of English syntax. And here we have the most obvious one, attending objects to the verbs. They give a lot more than just these two, like a lot more. And here's the one which I find the most interesting. So it's not as good at it, even though like it's not specifically trying to be good at it, but it's already quite okay, I would say, is that it's trying to see co-references mentioned. So he, she, and her are more or less the same, are referencing to the same things. Talks and negotiations are similar, but are still more or less referencing to the same thing. So yeah, so it shows that the theory has a really good, powerful understanding of language. So one could think, are you using BERT every day? Most of you are probably using BERT every day. It's probably the same for at least 1 billion humans in this world. And you're using BERT every day on Google search. And they actually wrote a blog post where they announced that they would start using BERT in blog posts. They would start using BERT in Google search. And here they give an example where they illustrate how this improves their search, so their search engine. And for that, here actually the word "to" has a very powerful meaning in the sentence, and especially the context of it. It has to be the context of it is also very important. Is the most important part here. And having a good understanding of "to" allows one to get a good result. And so we think that it might be BERT which is able to find a good meaning for the word "to." But in this blog post, they say that 1 out of 10 searches now made with BERT, and especially only the ones in English language, and the ones which have longer searches, which have more text in the search. And but they don't give any details sadly on how they do it, which model are they actually using, what data they pre-train on, because I guess that Google has access then way more data than just Wikipedia and the book corpus. They probably have some internal data sets which nobody has access to. And they don't show how they actually do the inference, because inference is already quite slow on BERT. So how do they do it efficiently for search? Because on search it has to be crazy fast. And so they don't give much details. So I hope you enjoyed this presentation with BERT. If you want to see, you have some sources. I have added all the sources which I used. You can you can access them. You fill the slides, and now if you have any questions about BERT, we still have 4-5 minutes for it, and I'm open to any questions about BERT or NLP more general, or about the transformer, and yeah, any of the steps, of course. So, any questions?